we're going to be looking at circle mensuration this lesson. And that word just means the part of geometry concerned with finding lengths, areas, and volumes. Before we do that, we're going to have to look at converting between radians and degrees. This process is actually really nice if you understand what radians and degrees really represent. I know in a full revolution that 360 degrees is equivalent to 2 pi radians. Now you could write 2 pi rad, or you could write 2 pi with a little c there, but often we know when something is in terms of pi that it is radians. If you had something like 0.579 ... or just 0.579, you would have to be clear that that was radians by putting a c or a little rad there. When we've got things in terms of pi, we generally can assume that it's radians. That also means that 180 degrees is the same as pi radians. We just divided both sides of that equation by 2. So that means to go from 180 degrees to get to radians, we'd have to do 180 times 180 over pi to be able to achieve that. I know that I would cancel off 180, so I know that the unit I'm cancelling off, degrees, needs to be on the bottom of that fraction here. So we're going to put that in there in a second, and the unit that we want to convert to, radians, is on top. So to go from degrees to radians, we multiply by pi on 180. To go the opposite way, to go from radians to degrees, you could divide by pi on 180, or you could just multiply by the reciprocal, 180 on pi. Again, we're going to degrees, so that's on top of the fraction, and we're going away from radians, so that's on the bottom of the fraction to cancel out. Let's do a couple of quick examples. Okay, we've got 60 degrees here, and we want to convert this. To convert from degrees to radians, we said we had to multiply by pi on 180. We can cancel this off here, 1 and 3, so that's the same as pi on 3 radians. Now you could do the same process here by multiplying by pi on 180, or you could recognize that 30 degrees is half of 60, half of pi on 3 would be pi on 6. Either of those approaches would be fine. The next one, we're going from radians to degrees, so rather than multiplying by pi on 180, we're doing 180 over pi. That's great, we cancel off those pi's. 180 divided by 4 will be 45 degrees. So why bother talking about radians? Well, the reason is we're going to be using them in our circle mensuration formulae. Now, the really critical thing you need to remember about this is for any formula where an angle is not trapped within or inside of a trig function, the angle must be in radians. So for me, to avoid any mistakes, I just convert all of my angles to radians regardless of what formula I'm using, because I'm less likely to make an error. We're going to be looking at some different things that we can calculate within circles. And to do that, we're going to have to look at arc length, chord length, and later on area of a sector and area of a segment. Okay, so an arc length that you're probably very familiar with is the entire circumference of a circle, which would be 2 pi r. But an arc length, and we're going to use the letter L, it's that weird curly L, it might look like an E, I'll try and make it clearer. L, we want to find a fraction of that total circumference. So we can multiply that with the fraction of the circle that is relevant. Now remember here we said we wanted everything to be in radians. So if we had a fraction of a circle, rather than thinking theta over 360 degrees, we'd be thinking theta, our angle, over 2 pi, and that would give us our length here, because it's a fraction of the circumference, the arc length. If you don't remember the parts of a circle that we looked at in geometry, our previous topic, I really recommend that you go back and look at them now. So let's simplify down this fraction a bit. We've got 2 pi that we can cancel off, so the arc length formula, L, is just r theta, remembering theta is in radians. So what we have here is our circle, and we've got our value theta, and this length along here would be the arc length L, remembering theta is in radians. Okay, let's go ahead and derive our chord length formula now. So we've got a circle here, we've divided it up into a sector, but we actually need to put a chord in for this to be relevant. So we're going to draw a straight line from this point here to this point here. Awesome. So that's our chord here. Now we want to be able to determine this length. So let's put some labels here just so you can be clear about what I'm talking about. We tend to call the center of the circle 0, and we'll call this A and B. In order to find the length of this chord, there are actually a few ways of doing this. Here's just one. you could divide this triangle OAB into two right-angled triangles. So we've got our triangle OAB. I've just drawn it on the side here. I've labelled in the radius, and I've put in a point P, which is the midpoint of AB. Due to a geometry rule, if you have a line from the centre meeting a chord, it then bisects AB. So P is definitely our midpoint, and the other part of that geometry rule is that needs to be a right angle. So we know that that's a right angle for sure. Now, is there anything else we can label in these triangles? Hopefully you recognise that this angle here is now theta on 2, because we said things were bisected here. So, using a bit of SOHCAHTOA for our newly formed right-angled triangle, so I'm going to write for triangle OAP, we're going to be using SO of our SOHCAHTOA fame, so sine x rather than theta, just so it's clear, is opposite over hypotenuse. And let's call AP, I don't know, let's call it Y. So, sine of our angle, theta on 2, is going to be our opposite side Y over R. So that means Y is going to be R sine theta, not sine theta, sorry, it's going to be sine theta over 2. Y is equal to AP, but we want AB, so AB equals 2 lots of AP, which is 2 lots of Y. So that means AB, the length of the chord that we're after, is going to be 2R sine theta over 2. And that's the length of our chord. So let's write chord length. Okay, that's the next formula that we'll need. Before I move on to the next derivation, I just wanted to make clear, because theta is trapped within a trigonometric function here, you could technically use either degrees or radians. But like I said, I often prefer just to work in radians for these style of questions, just so I don't make an error. Let's go into area of a sector next. Okay, let's do the area of this sector now. You could, of course, use what you learned probably in Year 8 Maths, theta over 360 times pi r squared. That's perfectly fine with me, but if we wanted to do with the fact that theta was in radians, we could do theta over 2 pi times pi r squared, and that would be the area of the sector. So I'm going to write A sector, I'll put that out the front, A sector for the next line. We could cancel off those pi's, so we could write that as a half r squared theta. You could have written it as theta over 2r squared, that's also fine. This just tends to be how it's written. Okay, the area of the segment is probably one of my favourites. I just think it's really cute. Remember, a segment would just be a portion of the circle that's been cut off by a chord. So let's draw a diagram of that. Okay, so we now want to find the area of this minor segment. This is actually one of my favorites, and I think it's super cute. Oops, I've just erased my entire circle. There we go. In order to do this, we can actually use the sector formula that we used before. So that would find the area of this sector here, and we could subtract this triangle here. And that would be like really helpful. So to do that, a segment. I'm just going to write a seg because I can't be bothered writing segment. So the area of the segment is going to be given by a sector minus a triangle. The area of the sector, making sure that this is the angle of interest here. A sector we said before, remember theta is in radians again. Really important for this formula that it is in radians because we're about to use a half r squared theta. If theta was in degrees, that equation doesn't make any sense at all. Now, the area of this triangle, we've got 2 radii here and we've got an included angle. And hopefully you remember the area of a non-right angled triangle when you know 2 side lengths and the included angle was a half BC sine A. So that means we can do a half minus a half because we're taking away the area of the triangle. The 2 side lengths is r times r, so r squared, and then sine of the angle, which is just sine theta. And let's take out a half r squared as a common factor. A half r squared, we're going to get theta minus sine theta here. Critical that you have theta in radians because we have an angle here that is not trapped within a trigonometric function. So we need to have that in radians. So that is our final formula. And let's put a segment over there, a segment. So we have learnt all of our required formulae here, remembering, don't forget, theta in radians. So if you're working on your calculator, you need to make sure you're in radians. That could obviously be standard or decimal, depending on the kind of question that you're doing.